In this particular lesson of graphing rational functions, we're going to be looking at other forms of rational functions. In the first two lessons, we looked at transformational form. It was very easy to determine the vertical asymptote, horizontal asymptote, and all the characteristics, as well as graph the function. In these examples, we are going to be looking at terms that have, or functions that have linear terms only. So if we only have linear terms, our equation will be y equals ax plus b divided by cx plus d. So we've got coefficients in front of each of the x's in the numerator and denominator, and we have constant values b and d. So we've got variables in both the numerator and denominator instead of just in the denominator. We're going to use those values of a, b, c, and d to determine the characteristics such as the vertical and horizontal asymptotes, the domain, and the range. So stuff that we've already talked about and that we can still make connections to, but just another way of looking at it if the function's given to us a little bit differently. So in order to determine the vertical asymptote, if we're in this form, y equals ax plus b over cx plus d, we first need to set the denominator equal to 0, okay? We can do that to get any vertical asymptote. So then we'll solve for the variable, and that will give us the value of that vertical asymptote. When we're in this form, we can take the opposite value of d and divide it by c, the coefficient of x in the denominator. Okay, so here's our example. Determine the vertical asymptote of the function y equals 2x plus 1 over x plus 3. So if I'm using the form where I take the opposite of d and divide it by c, d is 3, so its opposite is -3, and the value of c in front of the x in the denominator is just a 1. So x would just equal -3 over 1, or -3. Okay, you can use that method, or if it's easier for you, then you can set the denominator equal to 0, x plus 3 equals 0, and solve for the variable. That gives us x equaling -3. Okay, so you have your choice, whichever way. If you catch the shortcut way, the opposite of d over c, do that. If you like to solve equations, do that. Whatever works for you. The next thing we're going to determine is the horizontal asymptote. So we're going to look at the degree of the function. Okay, so in other words, looking at those exponents in the numerator and denominator. If the degree is the exact same value for both the numerator and denominator, then we're going to divide the leading coefficients. Okay, so we're going to look at those linear terms, the terms with the x's in the numerator and denominator, and we're going to divide the coefficients, the numbers in front. In this form, it's going to be, the horizontal asymptote will be the value of a over c, y equals a over c. Okay, we have the exact same equation, y equals 2x plus 1 over x plus 3, and we're looking at the degree. I have a 2x, that's x to the first power, over x plus 3, that's x to the first power in the denominator. So they have the same power, so I'm just going to divide those coefficients. 2 over 1, which equals 2. So the horizontal asymptote is y equals 2. We only do it this way when they have the same degree. That can be linear, quadratic, any power, as long as it's the same degree for each of those terms. And then determining the domain and range when our rational function is in this linear form, y equals ax plus b over cx plus d. We first need to determine our domain and range by using the vertical asymptotes and horizontal asymptotes. So in order to get the domain and range, I've got to know how to do the asymptotes, which we just practiced in the previous examples. So here's our example. Again, the same function, y equals 2x plus 1 over x plus 3. When we determine the vertical asymptote, we set the denominator equal to 0, or did the opposite of d over c to give us x equaling -3. We then determined our horizontal asymptote by doing the coefficients of the x terms because they have the same degree. So 2 over 1 gave us y equaling 2. Okay, so remember, our vertical asymptote splits the domain. The domain will go from -∞ to -3. union negative 3 to infinity. And the horizontal asymptote splits the range. So our range will go from bottom to top, negative infinity to 2, union 2 to positive infinity. So determine those vertical and horizontal asymptotes first so that you can get your domain and your range. All right, we're going to go through a few examples and see if we've gotten this down pat. Example 1, y equals x plus 1 over x plus 3. Determine your vertical asymptote. So we're looking at the denominator of the function, set it equal to 0 and solve to get x equaling negative 3, or you can use the shortcut method. Remember, this value splits our domain. So our domain is going to go from negative infinity to negative 3, union negative 3 to infinity. All right, now determining our horizontal asymptote. These numerator and denominator terms both have a power of 1. They each also have a leading coefficient of 1. So our horizontal asymptote is 1 over 1, which is y equals 1. That value splits the range from bottom to top. Negative infinity to 1, union 1 to positive infinity. So once you've got asymptotes down pat, domain and range is a piece of cake. Let's try some more. Number 2, y equals 2x plus 1 over 4x minus 6. Determine our vertical asymptote, set the denominator equal to 0 and solve, or do opposite of d over c. That'll give us 3 over 2. That would be a negative 6 or a 6 over 4, or solve that equation. That will split our domain from negative infinity to 3 halves, union 3 halves to infinity. Now we're going to determine our horizontal asymptote. Remember, as long as the degree of the x's are the same, then we're going to divide the leading coefficients, 2 over 4. Y equals 1/2. Remember, 2 over 4 simplifies to be 1 over 2. This is the value that splits our range from the bottom to the top. Negative infinity to 1/2, union 1/2 to positive infinity. Example 3. Determine your vertical asymptote so you can determine the domain. Set your denominator equal to 0. X minus 7 equals 0, so x will equal 7. That splits our domain from left to right, negative infinity to 7, union 7 to infinity. We're now going to determine that horizontal asymptote by looking at the coefficients of those terms, the negative 3x over x, because they have the same degree. That'll be negative 3 over 1, so y equals negative 3 for the horizontal asymptote. That value breaks up the range, bottom to top, negative infinity to negative 3, union negative 3 to positive infinity. And our last of these particular examples, I think we've kind of gotten it down pat by now, but let's practice one more, make sure we got it. Determine our vertical asymptote. Set the denominator equal to 0 and solve. We would subtract 2 and then divide by negative 5, giving us a positive 2 over 5, or x equals 2/5. This value splits our domain from left to right, negative infinity to 2/5, union 2/5 to positive infinity. Look at those leading coefficients of your linear terms, 4x over negative 5x. Remember, they have the same degree, so you can divide those coefficients. 4 over negative 5 is negative 4/5. The negative just applies to the entire fraction. So our horizontal asymptote is y equals negative 4/5. And then our range is broken by that value, negative infinity to negative 4/5, union negative 4/5 to positive infinity. Again, ranges from bottom to top. All right, we have just a few more examples to tie in some other topics that we've talked about so far in these lessons. We're still going to look at vertical and horizontal asymptotes to determine domain and range. This one also asks us for the end behavior. So our vertical asymptote for example 5, f of x equals x plus 4 over 4x minus 12. Set that denominator equal to 0 and solve to give us 12 over 4, which is x equaling 3. So there's our vertical asymptote. We see it graphed, but we can sketch it as well. That breaks our domain from negative infinity to 3, union 3 to infinity. So as I go from left to the right. All right, our horizontal asymptote. The two terms with the variables x and 4x have the same degree, so we can divide the coefficients. It's a 1 over a 4. So our horizontal asymptote is y equals 1/4. And we do see that dotted line really, really close to the x-axis. So it's a teeny bit above. That splits our range from bottom to top. So it'll go from negative infinity to 1/4, union 1/4 to positive infinity. All right, now dig back in your brains. What did in behavior mean? It says look at the far left side of the graph, all the way on the left. As x's approach negative infinity, as the function goes to the left, the y values approach, that's right, the value of the horizontal asymptote, 1/4. And the far right side, as x approaches positive infinity to the right, again, f of x, or those y values, approach the asymptote, that horizontal asymptote, at 1/4. We got it. We're rocking it. Number 6, final example. Determine the requested characteristics of our function f of x equals 3x plus 3 over x plus 2. Our vertical asymptote we find by setting the denominator equal to 0 and solving to give us x equaling -2. And we do have that already sketched, but we'll go over it again. This splits the domain from left to right, from negative infinity to -2, union -2 to positive infinity. When we look at the horizontal asymptote, we're looking at the coefficients of the variables. They have the same degree, so 3 over 1 will give us y equaling 3. There's our horizontal asymptote at y equaling 3, and it breaks up the range from negative infinity up to 3, and then from 3 to infinity. Now we did already see that little thing highlight that section. That is an interval of increase. The function from negative infinity to -2, we've got to know the domain in that vertical asymptote to help us with intervals of increase and decrease. So from negative infinity to -2, that function is increasing. When we look on the other side of the function's vertical asymptote at -2, from -2 all the way out to positive infinity, the function is still increasing. So that entire domain represents the function's interval of increase. Negative infinity to -2, union -2 to positive infinity. Since the function is only increasing, we will say there is no interval of decrease. Great job through this lesson. Let us know if you have any questions.